Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on convergence of the series and how to accelerate them. And in the last video, we talked about how to use sequence transformers, some transformation on the sequence, so that we get a better or a faster convergence. And the idea was that we start with the sequence an and create a new sequence bn from the terms of an, such that the limit of bn minus an minus a when n goes to infinity is 0. Now the assumption is that the sequence b also converges to the same number as a. That's the prerequisite. And then if this limit is 0, this means that bn, the series b, the sequence b, has a faster convergence than a. And we discussed multiple transformations, and the two famous ones were Aitken transform or delta squared process, and then the Shanks transform, which is basically the same as Aitken, all right? And Aitken takes the sequence and then calculates the first difference and the second difference, so delta of xn plus 1 and delta of n. And the difference, which is typically the forward difference, is an plus 1 minus an, all right? And then we said that we can, when we do this, the sequence becomes a new sequence. Here S is Shanks. So we said that we can transform that sequence, and typically we use these transforms to calculate series, which are the partial sums of a sequence. So we said that if we start with an, then we define a partial sum sequence, which is summing over the small a sequence. And then now we can transform this partial sum because we want to find if this series converges, we want to find the value of the series or the limit of this sequence, the partial sum sequence. And we said that we can transform using Shanks or Aitken. And then we can also apply Shanks or Aitken multiple times, because once we transform the sequence, it gives us a new sequence, and that new sequence also converges to the same limit, to the same value as the original sequence. And if I Shanks it again or Aitken it again, the new sequence, again, it should converge to the original value, but in a faster rate, all right? And we look at one particular example, which we already knew the exact solution. So the series was 4 times minus 1 to the k, 1 over 2k plus 1, and we summed it from 0 to infinity. And we plotted the error, basically the error of a partial sum with the exact value pi. And we summed up to 20 terms. And we saw that if we just sum this sequence by itself, the convergence is very, very slow. After 20 terms, summing over 20 terms, the error doesn't even have 1 decimal accuracy. And then as soon as we Shanks it, after 20 terms, we get 3 to 4 digits of accuracy. If we Shanks it again, the error even becomes better. And if we Shanks it 3 times, after 20 summations, the error is very, very good. So the convergence becomes faster and faster, all right? And we also discussed how we implement that in Java. And the idea was that, okay, our sequence was defined as a functional interface. So in order to keep that definition, the functional interface definition, we need to add a default method to evolve the interface. And the default method should return a new sequence object, because then we can easily just apply these transforms as many times as we want, because when we transform the sequence, the result is a new sequence, so we can transform it again. And but another thing is that sometimes when we're trying to apply Shanks or Aitken, they are not effective. And the general idea is that the Shanks and Aitken are good when the sequence is oscillating. Basically, it has a -1 to the n terms. So the terms of the sequence are oscillating between negative and positive. And basically this sequence that we already looked at has this behavior. It has a -1 to the k term, so the terms are oscillating back and forth between positive and negative, and Shanks and Aitken are pretty good for this type of sequences. But if the sequence is not oscillating, let's say all the terms are positive or negative, then typically Shanks and Aitken, they don't work well. They don't give you a very fast convergence. And in those cases, we typically use Richardson transformation. So the Richardson transform is a better way for non-oscillatory sequences, all right? And let's say we have this A sequence and we're trying to sum it up. So Sn is representing the partial sum from 0 to n. And the value of, and let's say we know that this series converges. So the value of the series, let's denote it by S, and we're looking for that. And the way we want to find it is just accelerate the convergence of this. All right. So the first Richardson transformation is take the Sn and Sn plus 1 and multiply Sn plus 1 by n plus 1, and then multiply Sn by n and subtract it from n plus 1 times Sn plus 1. All right. And here's the basic Java code. This is a default method in our sequence interface, which returns a new sequence object, and n goes to n plus 1 times the evaluate method at n plus 1 minus n times evaluate at n. All right. And then we can continue this with like the second order Richardson, which works on Sn, Sn plus 1, Sn plus 2. We can work with the third order Richardson, which works on Sn, Sn plus 1, Sn plus 2, Sn plus 3. And we can work on the fourth order Richardson, which is Sn, Sn plus 1, Sn plus 2, Sn plus 3, and Sn plus 4. And basically increasing the order of Richardson increases the rate of convergence. And as a general rule, I want you to remember this, really understand this. If you are given a sequence, straight up summing the terms of a sequence is always a bad idea, because most of the sequences that we deal with, especially in the engineering problems or physics problems, have a very slow convergence rate. So we just don't want to sum it up. I mean, the information is in the series, right? So, but the problem is that if we just sum up the terms of the sequence, we typically don't get good amount of information out of it. We have to sum a lot of terms. But because the information is still there, is already in the sequence, these transforms, Shanks, Aitken, and Richardson, they try to basically tickle the sequence so that you extract the information from the sequence faster and faster. All right. So if we go to Eclipse, to our sequence project, and in the sequence interface, I have already implemented the Richardson. So this is the first order Richardson, n plus 1 times an plus 1 minus n times an. The second order Richardson is half times n plus 2 squared an plus 2 minus n plus 1 squared n plus 1 times half n squared an. And then the fourth order, and then the cubic, the third order Richardson, and the fourth order Richardson. All right. And if you recall, we had all these methods: add, subtract, multiply, and divide, and negate, to add the capability of operator overloading for our sequence. So now if we use the plus operator on two sequence, the result is another sequence. All right. So that makes some of the calculations in terms of writing the code easier for us. All right. Now back to the PowerPoint. So let's look at this example, 1 over k squared and k from 1 to infinity. We already know that this sequence converges, because if you look at the error is summing from some n to infinity of 1 over k squared. And you can make it equivalent to an integral of 1 over x squared from n to infinity. That gives you a behavior of 1 over n. So we know that the error goes to 0. So this series should converge. And And the good thing is that we already know the exact value for the series, which is pi squared over 6. This is a very famous series, okay? And the behavior of the error is the limit plus a1 over n plus a2 over n squared, etc. And all these a1, a2 are most likely positive. A1 is definitely positive, right? We already said that if you estimate the error by approximating an integral of 1 over x squared, you get 1 over n, all right? Now this series is not oscillating, is not alternating sign between -1 and 1, so it doesn't have a -1 to the n sign, -1 to the k term, which means most likely if we apply Aitken or Shanks, we don't get a good convergence or a good acceleration. So let's try to actually see this in the code. So in the test, I'm going to create a new class called test Richardson, all right? And in the main method, I'm going to invoke test1, and test1 is going to basically be applying the Shanks or Aitken to this sequence. Public static void test1, and we're going to apply Shanks. So in order to do that, I'll go back to our basic code that we had before, and let's copy maybe this one, this code here. Let's change the sequence to 1 over k times k, all right? So we're looking at 1 over k squared sequence, and the exact result is math.pi times math.pi over 6, all right? And then if you recall, the way we calculate the partial sum is so it's going to be a sequence object. N goes to, this is a lambda expression, n goes to, we call the series class and called its static sum method. We pass in the sequence, so this sum method basically takes the sequence, initial and last, okay? We're summing from 1, not 0, to n, all right? And this gives us the partial sum. And then we're going to Aitken it, Aitken, so let's call it A. And then let's just rename this, refactor, rename, Aitken 1. And this is going to be Aitken, maybe also refactor, rename it, refactor, rename, Aitken 2. And this one is going to be Aitken 3, Aitken 3, all right? So Aitken, 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 and as we discussed, Aitken and Shanks are, so I'm going to call this AN to make it more readable. Aitken, 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 okay? So we create our partial sum, we Aitken it, it returns a new sequence, and Aitken it again, new sequence, and then Aitken again, and then Shanks 1 sum, let's also refactor, rename it. This is going to be Aitken 1 sum, and then this one is going to be refactor, rename. This is going to be Aitken 2, Aitken 2, and this is going to be Aitken 3 sum, all right? So everything is there, and then we're looking at the log. We're plotting in log scale because we want to look at the decimal places of the error. And again, Aitken 0, 1, 2, 3, okay? So everything is set, and let's run this to see what happens. Yes. Now, because I'm running this for the first time and I am using a Mac machine, I have to go to the arguments here and uncheck this flag, so that it can create a Let's try it again. Yeah. Okay, so we here let's see what happens. This is our original sequence and the convergence is not good, right? After the 30 I'm summing over 50 terms, and actually let's so index 0 is 1. Okay, we're summing from 1, so that was fine. So this is the original sequence, or 8can 0. We're not doing any 8can transform, and the convergence is very poor. We're not even getting a 1 decimal place of accuracy. And then the first 8can, second 8can, and the third 8can, they basically don't do any good, right? The only thing here is that after 3 8cans and 50 term summation, we end up between 1 and 2 decimal places of accuracy, which is very bad. It's like terrible, okay? And now let's try to do the same thing here. So I'm going to copy this, and let's call this test 2. And instead of 8can, we're going to do Richardson. Okay, and then so we're going to take R and then Richardson it, and instead of Richardsoning the new one, the new Richardson, what I'm going to do is I'm going to apply a second order Richardson to the original. So let's call this R2. So what I'm going to do is taking the partial sum and then Richardson second. So this is second order Richardson. Let's rename it. So this is Richardson 1, and this is going to be Richardson 2, and finally instead of Richardsoning the previous ones, I'm going to apply a Richardson 3 to the original sequence. So what we're going to do here, we're going to take the partial sum and Richardson 3. All right, and let's call this Richardson 3. So we have our partial sum, Richardson 1, which is a first order Richardson, Richardson 2, which is a second order Richardson, and Richardson 3, which is a third order Richardson. And let's rename these to Richardson 1 sum, this one to Richardson 2 sum, Richardson 2 sum, and this one to Richardson 3 sum, Richardson 3. All right, so everything is set. We're still looking at the log scale, and let's run test 2. So remember, test 1 was doing 8can transform, and test 2 is doing a Richardson transform. Wow, look at that. Here is the original sequence, which gives us about 1 decimal place of accuracy. The first Richardson, or the first order Richardson, gives us at least 2 decimal places of accuracy. The second order Richardson gives us 4 to 5 decimal places of accuracy. And then the third order Richardson basically obliterates the previous ones and gives us 3, 4, 5, 6, 7, 8, more than 8 decimal places of accuracy. Now, as you can see, this sequence was a monotonically increasing sequence, right? The partial sum. And the 8can or Shanks, they don't work because they're typically very good for alternating sequences. So let's do a side-by-side comparison here. Let's give this a title. So this is 8can, and this is Richardson. In the I have changed the Y label to Richardson. Richardson. Okay, now let's copy this and go back to PowerPoint. So we have this one, which is Aitken, and the other one, which is Richardson. And just a side-by-side comparison shows that how good Richardson is in terms of accelerating this non-oscillatory sequence to a very good convergence. Okay, so this is one of the very interesting things about these kind of transformations. Similarly, if you go back and look at the Euler transform also works on the oscillatory sequences. Now you might ask, why is it that we are so interested in oscillatory sequences? That's because most of the time in engineering problems or physics, when you try to approximate a function with a series, or the solution of a differential equation with a series, you most of the time end up with an oscillatory sequence. That's why a lot of thought has gone into developing these accelerations for oscillatory. Now you might ask, how do we come up with this transformation? Where is the root or basis of this Shanks or Aitken or Richardson transformation? How do we know why these transformations are in fact accelerating the convergence of the sequence? And this is the topic of the next video, so please stay tuned and subscribe. Thank you very much, and I'll see you in the next one.